In this video lecture, we're going to introduce and use the concept of small signal analysis in studying or analyzing a circuit that is linear other than for a one nonlinear element. The circuit we're looking at is a Thevenin network loaded by a nonlinear element x. We've chosen the relationship for that element, the VI relationship for that element, to be Vx is equal to k, 5 in this case, times the cube of the current. So the nominal voltage for Vs is the voltage source is 10 volts, and we have a Thevenin resistance of 5 ohms. And the problem that we're trying to answer is that if our voltage source is equal to 10 volts plus or minus 1 times sine omega, in other words, if we were to plot this over time, it would be centered at 10 volts, but it would sinusoidally, let me try that again, it would sinusoidally oscillate about 10 volts. It would go down to 9 volts and it would go up as high as 11 volts. And the question is, what is the response in the voltage that's across the nonlinear element? So we're going to use small signal analysis to help us out here. Initially this sounds like a pretty complicated problem, but it turns out to be quite simple. What we do is we decompose this problem into a operating point problem and a small signal problem. So we think of our input. I'm going to draw something general now. So if we have some system, call it some system t, and I have some input x of t, if I can express that as some capital X plus some little x, and by little x I'm going to put a little tilde over there. Alright, so in our case it would be like, here's something constant like 10, and something, the small part that moves about that large part is the 1 sine omega t. Right? Then we're going to say that the response can be decomposed into a constant or large constant part that is due to x. Okay, so this x input leads to this output y, plus some small response, what we call a small signal response. Small signal response. Okay. Now if the circuit or the system is linear, there is no problem in taking any input and actually decomposing it into smaller pieces and then just looking at the contribution of that particular input, each individual input, to the output, and then adding all of the individual outputs together. That's what we do when we do superposition analysis. So like if you have a circuit with two sources, you can turn one source on, calculate what the response is, the current or whatever you're looking for in some element, then turn that element off and that source off and turn your other source on and calculate the contribution. Then you add those two contributions together. Well, here we can do the same thing if it's linear. Okay, if it's linear. So system T here may not be linear in general, but we'll say it is a linearized system. Okay, and so this whole small signal analysis is the process of basically linearizing something that's otherwise nonlinear. And of course in our situation here we have one element, this element x, that's nonlinear, and we need to linearize it. So the nice thing about doing this decomposition is that you can consider the response just due to the little perturbation, and then add that to the constant response that you have from the constant input. So first off, let's solve this circuit for the case. Consider the case where Vs is equal to 10 volts. Okay. Now we had solved this before, and so I'm going to jump to it and just say let's try Ix equal to 1 amp. okay, which would give us, if we do KVL around the loop, we're going to have minus 10 volts plus 5 ohms times 1 amp, that's the voltage drop across the resistor, plus 5 times 1 amp cubed is equal to 0. And is that true? Yep, that's true, because it's minus 10 plus 5 plus 5 is equal to 0. Okay? So we have, therefore, I'll call this IX, capital IX is equal to 1 amp, and we'll say Vx is equal to 5 times 1 cubed, or 5 volts. Okay, so that's our, here we can say this is, let's say 5 volts. Okay, assuming this was Vx, okay, and assuming that this guy here is Vs, right, or I'm sorry, Vs right here. Okay, so if you put 10 volts in, you get 5 volts out. And now we're asking, what if we superimpose on that a small perturbation, a small change in the voltage? So I'm going to direct you to the notes. There's a more formal derivation, but here in this lecture I just want to kind of develop this through an example, because in the end, when you practice this, it's really simple, but when you go to derive it, it seems to just kind of bog down, and you know, students get confused over it. So what we're going to do is we're now going to look at a second input, this x tilde, if you will, and if the circuit is linear, which we will linearize it, then we can say that if we add a little input x hat or x tilde, then we'll get a little incremental output y tilde, and all we have to do is add that to the output that we already have, which is the 5 volts. So the question is, how do you actually linearize this? Well, if we go back to our IV curve for our nonlinear element, I have it plotted here, the blue trace. It's and I've denoted this operating point, basically the point at which, let me take this green off, that doesn't belong, the point, the initial operating point for the case where there's 10 volts. So what we have is IQ would be equal to 1 amp, and VQ, I'm using Q for operating point, that's a common letter that's often used. So when you just apply 10 volts to your circuit, you're going to be operating right here at 5 volts, 1 amp. Okay. Now, if you're going to move just slightly about that, so think about this for a moment. If we have a load line, let me draw I don't know if I have room for this, but let me draw the load line, and this would correspond up here to 10 volts. Now, if the 10 volts decreases just slightly, right, because this is going to oscillate between 9 and 11, if it goes down a little bit, what's going to happen is it's going to move down like this. The slope stays the same, because remember the load line, the slope is minus Rs. So this could move down by whatever our, call it Vs hat is, all right? And what happens? When it moves down, our operating point moves down to this new location, okay? If the change in the voltage source Vs is small enough, then the movement of the operating point along the nonlinear curve will be restricted to a small enough range that we can approximate that curve to be linear within that region. Okay, so what we do is we actually evaluate the slope of that curve evaluated at the operating current. Okay, the operating current being in this case 1 amp. Okay, so for our case, for this particular example, the derivative of 5I cubed is going to be 3 times 5 times I squared evaluated at 1 amp. And that will give us 15. And the units for this end up being ohms, because this has units of volts per amp cubed, and then we have times amps squared. So what we can do is we draw a small signal circuit, or a small signal model. Let's do that first for X, for our element X. So initially we had, this was our element, where you had Ix and you had Vx, and the relationship was Vx was Kix cubed. Now the small sig model is going to be nothing more than a resistor. We'll actually give it a letter. We'll say it's Rx, okay, because it has units of ohms. It's Rx. And the voltage that's developed across it now is Vx little tilde, and the current that's developed through it is Ix little tilde. Meaning that if the only current that's flowing through the element is the original non-perturbed, just the DC current, this 1 amp, then there's no voltage produced through Rx. Rx is there just to capture any incremental changes in the voltage Vx due to any incremental changes in the current Ix. And so we can use this, in the small signal circuit model. And this is what we'll analyze. So we go back and we draw the original circuit. The resistors never go away, so Rs stays there. But in terms of the voltage source, Vs, we're actually only going to be interested in our little incremental voltage source, right? We're only looking at how does the system respond to incremental changes about our 10 volt Vs. So we're not going to put the 10 volts in there, just the incremental part. And now we put Rx here, and the voltage that results is Vx tilde, and the current is Ix tilde. Now this Ix tilde does not represent all of the current that's flowing. It represents only the incremental current. So what we have is, if we put in Vs plus some, like capital Vs, plus a small vs into our circuit, what comes out is capital Vx. Okay, so what goes in is 10 volts, and what comes out is this 5 volts that we found, plus this incremental piece, which is Vx tilde. And how we find Vx tilde is simply from this small signal circuit, and it's a trivial circuit. We can write that Vx tilde is just the voltage division of our small signal excitation Vs. Okay, so we can write that if we put in a Vs, that's equal to our 10 volts plus an incremental Vs, what we'll get out is our operating point, or DC Vx, which we found to be 5 volts, plus Rx over Rx plus Rs times whatever that small signal input is. Okay, so back to our problem. We had Vs equal to 10 volts plus sine omega t. And the question is, given this, find, or what is Vx? Well, now we can write it. Vx of t is going to be equal to our operating point, big Vx, plus Rx over Rx plus RS times VS, little vs, which is our sine. This is going to be our little vs here. This is our big Vs, times sine omega t. And we can fill this out. This is 5 volts plus, and we had 15 ohms over 15 plus 5 times sine omega t. This is equal to 5 plus 3/4 sine omega t. So we find that if Vs is equal to 10 volts plus or minus 10%, right, then Vx is going to be equal to 5 volts plus or minus 15%. Now in this case I probably chose too large of a perturbation, so I actually had a 10% change in the input, and that's pretty large for being able to assume a small signal model. So if we were to compare this to the actual response, we would find that it has some errors. Maybe I'll put in a simulation result here to show you the difference. What would be more comfortable would be if the input may be changed by 1% or 2%, and we could say that the output would then change by 1.5% or 3%. My hunch is that at this large of an excursion, our linear model is not going to be accurate over that large of a range. Remember that the curve is nonlinear, and we have basically approximated it as a straight line. So the further you move away from the operating point, the more error that you have on either side. So you have to be careful not to assume a small signal at a given operating point about too large of an area. But as you can see, the actual practice of this is pretty simple. Let's do one other example. Okay, in this example, we're going to use a diode. Okay, and we have a voltage Vs and a resistance Rs, and we have this diode whose voltage is going to be equal to, or let's do it this way first. The current that flows, ID, is going to be equal to some scalar, this is a constant, times e to the Vd over NVT, and I will say, we'll call this 0.05. Okay, and let's put some numbers to this. We'll say this is equal to 10 to the minus 9 times E times 20 Vd. Alright, so what does this look like if you have Vd and ID? Alright, you end up getting this exponential curve. So, first what we need to do is we need to find what is the current that's flowing here. So if we said Vs was 10 volts and we had Rs was equal to 1 or 2K, okay, we'd have to find what that current is. Now, I don't want to go through solving what that current is right now. So instead, let me back off from this, and well, let's see here. I'll just leave this as IS, okay, and not put a number to that. And let's assume that the current that flows, the operating point current, is found to be 2 milliamps. Okay, so and if it was 2 milliamps, then that means we must have no, that couldn't be right. Let me take that back. Let's say it is 4.5 milliamps. Okay. Now that means that VD at this point would be equal to Vs minus Rs times ID, which is 10 volts minus 2 kilo ohms times 4.5 milliamps, which is 10 minus 9, or 1 volt. Okay? So I'm skipping that part of the analysis. We'll just assume that by one means or another you can find what that current is, or you might be given it as part of the problem. Now the real question is, if Vs changes by 1%, by how much does Vd change? All right. And so all we really need to do is we need to draw the small signal model, which it's always going to be a small signal resistor. It'll always be a resistor. And we will have some small signal input voltage, because that's what's changing. And we'll put RD for diode, a little r, and we'll have some small signal output. Okay, now we need to find what the little RD is. Remember, that is found by linearizing about an operating point. What is the operating point? It's at 4.5 milliamps. So first we have to take the derivative of the voltage with respect to current. Okay, well, when we look at this for the diode, we actually have the current with respect to voltage. So we can also write this as 1 over the derivative of current with respect to V. And that'll work for us, so we'll do that. And this is going to be at a voltage Vd equal to, what do we see, 1 volt. Okay, so that's 1 over, and then when we take the derivative of the diode current with respect to voltage, we're going to get 20 Vd times Is e to the 20 Vd. And this is evaluated at little Vd equal to our big Vd here, 1 volt. Okay, and so let's look at that further. This right here is just simply ID, our 4.5 milliamps. Right? Because it's just the diode equation evaluated for a diode voltage that's at 1 volt. Okay, so we'll have 1 over 20 Vd, this is going to be 1 volt, times ID, which is 4.5 milliamps. Alright, and that is going to equal, let's say, 1,000 over 90, or 100 over 9. Right? So 11.1 ohms. Okay, so here's what we have. We have 2K, that's 2,000 ohms, and we have 11.1 ohms. And if we put in some small change Vs tilde, we'll get some small change in the diode voltage, VD tilde, and it will be equal to 11, approximately 11 over 11 plus 2000, right, because of voltage division. And we're almost there. So we can say that if Vs changes by 1%, then VD will change by 2011ths of 1%, all right, which is about 0.5% of 1%. So is that it? Too many zeros there. 0.5% of 1%. I think I had another zero in there. Okay, let's do that again. 0.5%. Oh no, I did this wrong. So 1% times 0.05. Yeah. Sorry, 0.005%. Okay. Or otherwise put, if the voltage on the source changed by 10%, there would be 0.05% change in the diode voltage. So typically in these small signal analyses, you can be sure, actually, that every time when the small signal model to a nonlinear element is a resistor, you just have to find the slope at the operating point, replace the nonlinear element with the resistor. You turn off all of the independent sources like the DC sources and look just at the perturbing source. So in this case, you notice we got rid of the 10 volts, right? And the only thing we put in was the little perturbing VS tilde, and looked at what contribution it made to across the small signal resistance.